Thank you. So welcome. Today our key learning points are going to be the SiteHawk cable and antenna analyzer. We'll touch on some RF basics for antenna system troubleshooting. I'll go over the key measurements of the analyzer and also the importance of regular calibration and why we do it. When I get to the SignalHawk spectrum analyzer, I'll discuss what is a spectrum analyzer and also give you the key measurements. And then I'll talk a little bit about interference hunting and what is AOA, or angle of arrival. So the benefits of line and antenna sweeping are, first of all, is to test. And we test the overall integrity of an antenna system installation. And then we verify that the antenna system components meet the manufacturer's design specifications, and also verifies that the antenna system meets the system engineer's design specifications. We'll pinpoint the location of antenna system problems prior to usage, and then confirm that the system integration and antenna performance is what we expect it to be. So why do I need a cable and antenna analyzer? Well, first of all, we will do some system commissioning. And what that is a process whereby faults and potential faults are eliminated before they compromise the system prior to the system being put into use. It is structured and methodical, but also thorough, with the goal of having 100% system uptime for effective communications. We can also troubleshoot existing antenna systems. When there is a problem, quickly read the system and determine where the problem is. And we also can perform preventive maintenance, perform sweeps, compare to the sweeps saved during commissioning to see where changes may have occurred, and then fix potential problems before they take the system down completely. Some RF basics we'd like to touch on. All components in a feed line system, including the antenna, must be matched in their characteristic impedance. What is the characteristic impedance we are interested in? 50 ohms. Impedance matching, measure match, or simply match all refer to the same measurement. It is how well each of the components within a system are matched to the rest of the components. And this is measured in either VSWR or VSWR or return loss. Feed lines are designed for a specific impedance. Impedance is defined as the total passive opposition to the signal. Impedance is a function of the diameters of the center conductor to the outer conductor and the dielectric constant of the insulating material between them. Changes in any of these dimensions will change the impedance of the feed line. And understanding what causes impedance changes is halfway to solving feed system problems. One of the fundamental laws of physics states when load resistance or impedance is equal to the source's internal resistance or impedance, maximum power will be developed in the load. So basically what that says is when all the components in your feed system are matched, when you key up your radio or turn on your transmitter, all that power is going to get out to the antenna. Coaxial cable impedance is a complex function of the ratio of the diameters of the conductors. If the diameter ratio changes, the impedance of the cable will change and the power transfer changes also. And some of these things that will give us these changes are dents, kinks, any deformation of the cable, too sharp of a bend radius, etc. If the transmission line or your coax and the load or your antenna, if the impedances are not the same, meaning they're mismatched, power is reflected from the load in the form of a traveling wave back to the source. Waves moving in the other direction, they interact, resulting in a series of standing waves along the length of the transmission line. A short or open causes 100% of the power to be reflected. And this is measured in VSWR or return loss in dB or decibels. So what is mismatch? You have forward power going down the line, you have some sort of mismatch, and then you have a little bit or certain percentage of reflected power. You can think of it as a garden hose with no obstructions. With no obstructions, the water is flowing freely out the end. What happens when the hose is kinked or the transmission line is shorted? You really don't get much water flow. And this is how you can think of mismatch in a transmission line. So VSWR versus return loss. What is it? What does it mean? So a perfect VSWR is going to be 1.0 to 1. If we look at the return loss scale, a perfect return loss is going to be negative infinity. What this means is we have a perfect match. 100% of the power is delivered to the load or antenna. But this is not possible because all components in a system have a certain amount of loss. If we have a VSWR of 1.43 to 1 or negative 15 dB on the return loss scale, that tells us that there is very little reflected power. As a matter of fact, 96.84% of the power is delivered to the antenna and roughly 3% is being reflected back to the source. 1.5 to 1 VSWR or negative 13.98 or rounded to neg 14 dB return loss. Very little reflected power, 96% of the power is delivered to the antenna. This is great. 2.0 to 1 VSWR or negative 9.54 dB return loss. That means roughly 89% of the power gets delivered to the antenna and about 11% is getting reflected back. That's not quite as good as some of the numbers in the green above. Now, if we have a VSWR of 10.0 to 1, that equates to minus 1.74 dB on the return loss scale. This is a very poor match. Only 33% of the power delivered to the antenna and the rest is being reflected back. So what does this mean? You may have customers that you're trying to reach via the radio, or there's other areas or customers in outlying areas. They're not hearing your calls. So this is how a little comparison of VSWR versus return loss. So what causes an impedance mismatch? Bad or loose connectors, bad jumpers, water in the feed line, clamps tightened too tight, antennas installed too close to the tower or other antennas, corrosion, low quality connectors, dents in the feed lines, gouges, and my favorite, bullet holes in the feed line. I teach this class a lot and I always like to ask, can you add anything to this list? And I always do get some interesting answers. So measure match, this is one of our key measurements for cable and antenna analysis. Measure match determines if there's a problem with your system. System impedance versus frequency is plotted on the display. The results are in VSWR or return loss. Distance to fault or DTF. This will pinpoint the location of the problem. Distance versus frequency is plotted on the display. And again, we get our results in VSWR or return loss. And finally, we can do a cable loss measurement. We can determine how much power is being lost within the line or in individual components. The measurement may be called insertion loss, cable loss, or attenuation, and this is a manufacturer's specification. So if we were going to sweep an antenna, we'd be in measure match mode. Well, what do we need to do? We need to enter the frequency range of the antenna, set the range a little wider than the specified range of the antenna, calibrate your analyzer, attach the antenna, and what does the sweep show? It shows us the frequency response of the antenna. And here's a good sweep of an antenna. So if we pick this sweep apart a little bit, we can look down at the bottom and we can see that we're sweeping from 600 megahertz up to 1 gigahertz. I have a limit line set at negative 14 dB, and that's this red line. I've calibrated. My correction is on. I'll get into the calibration part a little bit later. And we can add a couple of markers, marker 1 and marker 2. And from this, I can see that at the low end, marker 1's at 781 megahertz, where it crosses the limit line, and where it comes back above, marker 2 is at 918 megahertz. And right in between those two markers, that is the antenna resonant band. Also note, I'm getting my results back in return loss. Well, what about SWR? This is the exact same sweep, except note that I've changed my mode from return loss, or my scale from return loss to SWR. The markers are in the same place, 781, 918. The only thing that has changed is our sweep looks a little bit different, which it will when you're in comparing VSWR to return loss. My limit line, which was previously at neg 14 dB, now it is at 1.5 VSWR, and everything below, showing the yellow portion of the trace, is passing. And this is in between those two markers. That's going to be my resonant band, or my usable portion of the antenna. So that's an antenna sweep showing the results in SWR, comparing it to the VSWR measurement. Cable loss is another measurement we do. So coax cables, connectors, and other devices have loss. It's due to the skin effect, radiation, leakage, conductor resistance, and dielectric losses in the cable. Cable loss is specified by the manufacturer, usually at 1 or 2 particular frequencies. So whenever you're checking on a cable, make sure you look at the manufacturer specifications for more details. Distance of fault, what is it? Or we call it DTF. It's a measurement of how far from the test point a fault occurs. Instead of hand-over-hand checking of the feed line up a tower, the analyzer will give a distance to the problem or fault. The field technician might still have to climb the tower, remove ceiling panels in a building, or crawl through tight spaces, but he or she will have a much smaller area to check to find the fault. So when you're doing distance to fault, what do we need to know? We need to know the frequency range of the system. We also need to know the cable type, and the SiteHawk has a list of predefined cables. There's about 94, 95 predefined cables that are in the cable list. So if you know what your cable type is and it's in that list, you just select it and we'll populate the proper fields. You also need to know the total length of your system. A diagram of your system is also helpful. So you have the frequency range of the system. When performing a distance to fault or DTF sweep, widening the frequency range results in a display with more detail visible. When measuring a transmission line with no frequency sensitive components attached, such as an antenna, a large frequency span is desired to help highlight potential faults or areas of performance degradation. When measuring an antenna system with an antenna or lightning protection attached, operating frequency must be used. So here's some frequency range tips. The greater the frequency span of measurement, the more detail will be seen in the display. The greater the frequency span of measurement, the smaller the maximum distance that can be measured. The maximum distance is inversely related to the frequency span of the measurement. In general, the frequency range should be selected for optimum resolution without exceeding the frequency range of attached components, while maintaining a distance large enough to see all antenna system components. And also add about 10 to 20% to the known cable length to your total distance. I mentioned the cable information. Cable type. There's two cable parameters needed. We need to know the velocity of propagation and the cable loss. The velocity of propagation is the reduction in signal speed as radio waves travel through a medium other than free space. It is also known as velocity factor. Entered incorrectly, it affects the distance of a DTF sweep. Cable loss. This is how much power is being lost within the line or in individual components. It may be also called insertion loss, cable loss, or attenuation, and is a manufacturer's specification. Entered incorrectly, it will affect the amplitude of a distance default sweep. Entering the wrong velocity of propagation or cable loss is cumulative with cable length and becomes more pronounced with distance, meaning the further away from the test port, the more error that is introduced. I mentioned it's helpful to have a system diagram, and I know it's not always possible. Without a diagram, it is difficult to tell what you're looking at, and anything you see is a guess. I also mentioned total length of your system, add 10 to 20% to the stop distance. This will allow the entire system and all components to be displayed on the analyzer. So when you set up for distance default, select the DTF mode by tapping up here at the top. And you'll see this drop-down menu to the right. Make your selection. You can select DTF SWR, which means you're going to set up for a distance default sweep, but your results are going to be in VSWR, or DTF return loss, which gives you your results in return loss. So now I have selected distance default. My units are going to be in return loss. Set the frequency range wider than the system requires. So in this case, I'm set from 1 megahertz to 4,500 megahertz. Select the number of data points, and you can select from 51 all the way up to 3201. The more data points, the more resolution. Set your DTF info. Set your units. You can have meters or feet. Set your stop distance. Add total length of the system, including the antenna, and add 10 to 20%. Enter the velocity of propagation and cable loss manually, or select the cable type from the cable list to populate velocity of propagation and cable loss fields automatically. Then calibrate. It's very important you do the calibration process. So, some typical values to remember, and this will become apparent a few more slides coming up. So, an antenna at resonance, typically the manufacturer will specify them at 1.5 to 1 VSWR or negative 14 dB on the return loss scale. Typically, a connector will come in at 1.12 to 1 VSWR or negative 25 dB on the return loss scale. Jumpers typically come in at 1.04 to 1 VSWR or negative 35 dB return loss. A lightning arrestor, 1.12 to 1 VSWR, negative 25 dB return loss. And finally, feed line, generally at 1.06 to 1 or minus 30 dB on the return loss scale. And as I mentioned, these are typical values. If you have a specific component, you would want to check the manufacturer's specifications. So here we have a test system diagram. I have my analyzer out here to the left. I have my RF test cable. Here's a connector, 33 foot of cable. They're joined together by a connector, another 33 foot of cable, a connector to the antenna with about 20 feet of coax. Total system length is 86 feet. The other thing to note when I'm using a test cable, if I calibrate to the end of that test cable, this is going to be 0.0, and everything back here is out of the picture. So here I have a distance default measurement. I know it's distance default because it tells me. I'm sweeping from 700 megahertz up to 900 megahertz. I have 801 data points set. My stop distance is set to 100 feet. Remember in the previous slide, my total distance was 86 feet. Well, I add about 10% and I 10 to 20% final total distance, and I've settled on 100 feet for my stop distance. There's a little indicator out here. This is telling me the distance default, the maximum length I can see is 1,750 feet. And this is all based on my frequency span, the number of data points, and the cable information, most notably the velocity of propagation. So let's take a look and see what we have. Marker 1 out at 0 feet. That's right here. It's right on the end of the scale. That was that very first marker or very first connector at the end of my test cable. Now I move along down here nice and low. The other thing I want to point out, marker 1's at minus 44 dB. And if you remember from that table of typical values, connectors come in at about neg 25. So this is down at neg 44. So you can see this is well below the neg 25. So this is a good connector. The next point is my feed line. And I said the feed line wants to be at about minus 30 or so. And I can see that I'm down about neg 57. So I'm well below that neg 30 dB. Now, remember in that diagram, we had two pieces of cable joined by a connector or a non-precision barrel in this case. And if we look at the marker 2 value, it's at 34.5 feet at minus 41. So we've identified that second connector. Then we have the feed line, the second length of feed line, followed by the connection to the antenna. And we can see marker 3 is at 67 feet and marker 4 is at 86 feet. And we have all the amplitude values shown. So this is a decent sweep of that test system we had. Now, wait a minute. What is this? This is something I did not see in the diagram. We had the first connector, the second connector, the third connector, and the antenna. But this was not in our diagram. And the reason the diagram is important, this tells you something is out there. So you would actually physically have to go and take a look. And all we know, we go out and take a look and it is some sort of a fault. And in this case, the fault on that previous slide ended up being a very large dent in the cable. Now, if you don't have a diagram and you need to know, hey, where's the end of my transmission line? We can still do it. You have your analyzer set up, a couple of connectors. We see our feed line. But if you open up one of the connectors and put a short or an open out there, you're going to get full reflection. And now marker 2 shows us at 34 feet, I'm at about 0 dB. And as I mentioned previously, anytime you have a short or an open on the line, it's going to be pretty much 0 dB. So here we've located the end of our transmission line, and to double check to see if I have it right, now if I put that precision load on the end, it drops it down very close, neg 40. So that's how you can tell if you are in the end of the cable like you think you are. So some tips for setting up a DTF sweep. What if I set a stop distance more than 17, or why can't I set a stop distance more than 17.49 feet? Well, I mentioned the max distance the SiteHawk can see into a cable is based on the frequency span, the number of data points, and the velocity of propagation. So the first thing I'd want to do, notice I have a very wide frequency span, 1 megahertz up to 4.5 gigahertz. And if I tap where it says start, now I can set my frequency by center frequency and span. So here, all I want to do is narrow my span a little bit. I can also set my data points to 201. My velocity of propagation is set at 0.8, and I can't really change that because that's a manufacturer spec. All of those tell me with these settings, I'm at 17.49 feet. So the one thing I can do, I can't change the cable spec, but I can either increase data points or narrow my span. So if I increase the data points to 401, notice my distance default has increased to 34.98 feet. If I increase again to 801, my max distance goes to 69, almost 70 feet. Now, if I narrow my frequency span down to 1,000 megahertz, now I've increased my distance to 314 feet. If I narrow the frequency span to 400 megahertz, I increase to 786 feet. So by adjusting the number of data points and decreasing your frequency span, you can actually lengthen how far into a cable you can see. I mentioned calibration. Accurate measurements can only be taken with the analyzer if the calibration is accurate. The calibration tells the unit where to begin the measurement. And once you set the unit up, set up your frequency range, set up all your DTF information, calibrate, and it is going to set all the cal factors that it needs. So the calibration also defines where the SiteHawk ends and the attached system begins. So use a test cable in your measurements. Adding a test cable allows you to extend the test port to get to those to reach those hard to get places. The addition of a test cable or changes in the length of the test cable will affect readings taken in distance default measurements. So whenever you're using a test cable, calibrate to the end of the cable. Is there any questions? Or should we just keep moving? I'll keep moving.
I'm sorry, Greg. No, there's no questions at this point.
Okay, great. Then we'll just keep on going, save the questions for the end.
Perfect.
So, spectrum analyzer basics. What is a spectrum analyzer? We'll go over some key terms and analyzer basics, and then we'll discuss a little bit of interference hunting and what is angle of arrival. Well, what is a spectrum analyzer? It is a receiver that displays the received signals on its screen as amplitude or power versus frequency. Provides an effective insight into RF performance of a system, analyzes radio frequency spectrum, and measures intended and interfering signals. Also allows setup of parameters such as frequency, amplitude, and markers. And graphically displays signal amplitude versus frequency and saves traces. It can be portable or standalone bench equipment. So why use a spectrum analyzer? Well, we can do an off-air signal test. We can do interference mitigation. Look for harmonics, noise. We can look at the frequency spectrum signal to identify signals below. We can look for noise, which is going to be any unwanted signal. Harmonics, RFI, radio frequency interference, which comes from thermal noise, shot noise, transistor noise, or atmospheric noise. And we can also look for intermods or intermodulation, a signal that results from the mixing of two or more RF signals. And then we can look for noise floor. So some definitions. Harmonics are unwanted signals. They interfere with communications. They're produced in nonlinear amplifiers, components, etc. They're on whole number multiples of frequency. And harmonics are not always unwanted. Sometimes you're making a frequency doubler, tripler, etc. Harmonics are whole number multiples of a frequency. The first harmonic is the frequency, also known as the fundamental. So 1 times 800 megahertz is 800 megahertz. The second harmonic is double the original frequency, or 2 times 800 meg is 1600 megahertz. Third harmonics is 3 times, or 3 times 800 is 2400 megahertz, and you can just keep right on going. Harmonics typically do not cause system degradation in the system, causing or creating the harmonic content, but will cause problems for other systems using the frequencies or channels the harmonics fall on. What is noise floor? It is the measure of the signal created from the summation of all the noise sources and unwanted signals within a measurement system, where noise is defined as any signal other than the one being monitored, including thermal noise. This is something produced from component heating. Cosmic noise, which originates outside Earth's atmosphere, similar to thermal noise. We have atmospheric noise, primarily from lightning, discharges, and thunderstorms. The lowest signal power level that can be measured when using a spectrum analyzer or other device. The noise floor defines the point at which a signal used in communication is no longer usable. RBW, resolution bandwidth, is the bandpass filter in the IF path. It determines the RF noise floor and how close two signals can be and still be resolved by the analyzer into two separate peaks. Adjusting the bandwidth of this filter allows for the discrimination of signals with closely spaced frequency components while also changing the measured noise floor. Decreasing the bandwidth of an RBW filter decreases the measured noise floor and vice versa. The video bandwidth determines the capability to discriminate between two different power levels. This is because a narrower video bandwidth will remove noise in the detector output. It is used to smooth the display by removing noise from the envelope, which is considered helpful when assessing low-level signals. The lower the video bandwidth, the slower the sweep speed. The higher the video bandwidth, the faster the sweep speed. DANL, or displayed average noise level, is the minimum level that the spectrum analyzer can measure and reflects the internal noise level of the spectrum analyzer. It determines the sensitivity of the spectrum analyzer. To increase the sensitivity of the spectrum analyzer, adding a preamp with lower noise figure and attenuators reduce the noise figure of the spectrum analyzer. Lower resolution bandwidth leads to lower DANL. And SINAD is the signal to noise and distortion ratio. It is a measure of the quality of a signal from a communications device. SINAD is equal to P sub signal plus P sub noise plus P distortion divided by the noise plus the distortion, where P is the average power of the signal, noise and distortion components. It's expressed in dB, quoted alongside receiver sensitivity, and it's never less than 1. For example, a receiver sensitivity of 25 microvolts at 12 dB SINAD. The receiver will produce intelligible speech with an input signal as low as 0.25 microvolts. When you connect a spectrum analyzer, you can have an over-the-air connection via the antenna, or you can do a direct connection to a transmitter. The max input to the SignalHawk is plus 20 dBm or 100 milliwatts. If you have anything higher than that signal level, you need to put an attenuator on the test port, an attenuator, coupler, or signal sampler. So here's one example. We have a transmitter that's spewing out a signal. Out through the antenna goes the signal, and then in through the antenna on the spectrum analyzer, and in is where now we can see the signal. Or you can have a transmitter directly connected to the spectrum analyzer, but again, you need to have an attenuator if the signal is going to be greater than plus 20 dBm. And then using a coupler, you can still output to the antenna and still sample that signal to take a look at into the spectrum analyzer. So what is spectrum analysis? It allows us to look at individual signals, takes apart complex sine waves or multiple signals, looks at amplitude versus frequency, and allows us to look at a range of frequencies, cover a wide range, then narrow into our problem area. It allows us to check our own equipment. Transmitter, base station, repeater output. So here, my display is going to show frequency versus amplitude. Frequency is across the bottom of the display. Amplitude is up and down the left side. What you don't see is a waveform. A waveform or shape is seen on an oscilloscope. The other thing is the oscilloscope plots voltage versus time. So, have you ever heard stories on the news of people having issues with garage door openers not operating at certain times of the day? Maybe their key fobs were not operating. Maybe you've heard of the local police department complaining about their two-way radios being taken down occasionally. These are just a few examples of true stories where an RF interferer caused problems. Using an SH60S AOA can help you find, locate, and eliminate these problems. What is angle of arrival? It is the direction from which the RF signal is received. It is used to discover the location of interfering signals, such as unlicensed radio transmissions or other types of generators producing RF signals disrupting lawful transmissions. Angle of arrival uses a technique called triangulation, where a signal strength sample is recorded in different locations and the position is marked on a map forming a triangle. A minimum of 3 or more samples or vectors, they're recorded, and where they intersect, the interfering signal is found. So the 60S AOA is an advanced model spectrum analyzer containing interference analysis capability with mapping. Users can triangulate the location of an interferer based on power levels with a directional antenna. What do I need? Need to know the user's frequency of interest. I need to enable GPS, enable the Wi-Fi, and connect to a Wi-Fi network. Once GPS location is established, download a local map of the area. Some common interference sources are faulty or poorly shielded electronic devices, electronic devices configured incorrectly, electronic devices that are not compliant with local regulations, jammers, and deliberate interference. So what you want to do, ensure that GPS and Wi-Fi are enabled and connected to the internet. Then identify the signal of interest. Place a marker on the signal. Zoom in and center the signal of interest by narrowing the frequency range. Be sure to use a directional antenna appropriate to the frequency of interest. Then you want to get your map. So to get that, select AOA Locate from the Measurements menu. Wait for the SignalHawk to establish GPS position. And then the SignalHawk will download a map of the surrounding area. Align your antenna with the SignalHawk and press Start. Keep the antenna aligned with the SignalHawk and rotate until a consistent direction, shown in red, is established. Now press Save. The direction with the strongest signal strength will be shown as a black line. The relative strength and vector is displayed at the top of the screen. The latitude and longitude will be displayed at the bottom left. And then drive to a second location and repeat the exercise. Zoom out in order to see where the two vectors cross, and you can zoom in or out by just pinching the screen, similar to what you do on your cell phone. Both vectors are now displayed at the top of the screen. And notice that the first vector is now shown in red and the second in black. Drive to a third location and repeat. Based on the current estimated position of the signal, decide on a suitable third location. Drive to location 3, repeat the exercise. Note that the first vector is now shown in green, the second vector in red, and the third vector is black. You should now have a good estimate of the source of the signal. So what equipment is needed? Well, the frequency of the interfering signal must be identified on a spectrum analyzer. Using a directional antenna, GPS, and a mapping program, interfering signals are able to be searched for and found. An integrated or electronic compass is inside the AOA. It's very important that the antenna and the SH60S be oriented in the same direction. So if you can see over here in the photo, the test port is pointing this direction and the antenna is in the same direction. To effectively detect an interfering signal, you must have an antenna that is matched to the frequency of interest, preferably directional. So how do we do it? I'll walk through an example utilizing Bird's SignalHawk with AOA. Leverage mapping technology from OpenStreetMap, allowing users to triangulate the source. Easy to use interface to pinpoint potential in-band interferers for signals between 9 kilohertz and 6 gigahertz. The 60S AOA is portable, battery operated, and rugged for remote locations. So we'll walk through an example with the SignalHawk that we did at our own corporate headquarters. It's easy. Tips. Before using the AOA feature, be sure to download your map. So you'd have to connect up to the Wi-Fi in order to download the map. Note that you need a minimum of 3 vectors for a more precise location of the area of uncertainty. Densely populated areas will be more difficult to pinpoint due to building interference. And the result of triangulation is to help narrow down the target area. So verify an interferer is present, and then center the interfering signal. Zoom in on the interferer, and in this case, it appears to be at about 465 megahertz. Then you want to tap on the gears icon. Turn the GPS on. Verify the coordinates are locked. You need to have an outdoor line of sight. So you either need to be outdoors, near a window, or somewhere that the GPS satellites will be able to get locked on. And it may take 30 seconds or up to 2 minutes to lock. So then we would press measure, select AOA locate, press OK, and then your previously downloaded map appears, and you can update it by just pressing map. If you want to clear coordinates from a previous measurement, all you need to do is press reset. So you need the Wi-Fi to dynamically load the map or have map locations preloaded, and ensure the map of your required coverage area is displayed before venturing out. So it might be a low level signal that you're looking for, so you may have to turn the preamp, and we do this by tapping the preamp button. And there's 2 levels, select preamp 1 or 2, whatever's going to give you the stronger signal. And then press OK. I mentioned it uses the built-in GPS and a mapping program. Zoom in or out of the map by dragging and pinching with your finger and thumb. Invoke the signal strength measurement by pressing start. Keep in mind, you must have the GPS lock. And you can see that it's locked because the numbers are up here at the bottom. So point the antenna and the SignalHawk to find where the signal is strongest. Rotate in a signal while pointing. Continue pointing and rotating until the circle is complete. Mark your first vector by pressing save. And then you can also capture a screenshot by pressing the screenshot button. Repeat the previous steps to go to the second vector. So arrive at your second location, repeat steps performed to capture the first vector. Invoke the signal strength measurement by pressing start. Again, point the antenna and SignalHawk to find where the signal is strongest. Continue rotating in a circle while pointing and rotating until circle is complete. And then mark your second vector by pressing save. And you can also save a screenshot again, and this is just optional. And you'll see the second vector is saved on the map. Vector 1 is marked at -35 dBm at an angle of 125 degrees. And vector 2 is marked at -58 dBm at an angle of 94 degrees. Go to our third location and repeat the steps performed to capture the second vector. Invoke the signal strength measurement by pressing start. Point the antenna and SignalHawk to find where the signal is strongest, while rotating in a circle, pointing and rotating until the circle is complete. Mark the third vector by pressing save, and then save the screenshot if you like. And vector 3 has been saved, marked at -41 dBm at an angle of 194 degrees. So now our triangulation is complete. Now we can zoom in by pinching the screen. And one thing to note, you can have more than 3 vectors. As a matter of fact, the more vectors, the more narrowing down of the interfering signal location. Zoom in or out by pinching the screen, and I didn't go through the whole process, but we've added a few more vectors. And the interferer is within that red circle. So now you can invoke the audio feedback to pinpoint the source by tapping on the audio button, and then walk around pointing the antenna. And the audio tone is going to be loudest in the direction of the interferer. And then finally, you'll find where that interfering signal is coming from when that audio tone is loudest. Any questions? I know it was a lot of material on 2 different analyzers in a very short period of time to take in, but it's all important and all good.